So before we get into inverse trigonometric functions, let's just review a bit of inverse functions from our previous math class. So an inverse function, it's in the name of it, it inverts the function, basically switches how it operates. So say we have some function f of x, and typically we write it as y equals f of x. And the idea is that you input some x value, and then the function takes over, calculates, and the output you get is a y value. So you could think of this as like, say we had a function that worked with temperature, and you plug in some temperature in degrees Celsius, and the function worked, and it gave you the degrees in Fahrenheit. So you'd have this function that works to convert something for you, where you input one thing and get out the other. Now the idea with an inverse function is, what if we wanted to switch that operation? What if I wanted a function where I would plug in Fahrenheit and get out Celsius? So reversing what my input and output are, and that's where an inverse function comes in. What's going to happen is those input values become the output values, and the outputs become the inputs. So it's as simple as switching x and y. You could also think of it as switching the domain and range of our graph. That comes through as well. So those will switch over. So it was the domain of our original function will become the range of our new function, and so on and so forth. Now, in terms of notation, how we denote our inverse function, this is read as the inverse of f of x. So we denote that with this little -1 right here. How we read that is that it's showing an inverse function because the -1's inside there, or you could think of it as kind of attached to the name of the function. Something I always want to make clear is that that -1 there is not an exponent. It does not have the property of an exponent. It's just a symbol to represent the idea of an inverse. It's a function that took our original function f of x and flipped our inputs and outputs. That's what it's telling us. And I think I could almost safely say that when we're dealing with inverse trig functions, you shouldn't ever be using an exponent of -1. So if you start typing that into a calculator, pause, because it's most likely not the right thing to do. So this input function, and where this can be a bit confusing is we do write it as like y equals inverse f of x. However, in terms of the x values and y values of our original function, how it's going to work is that the input would be our original y values, and the output would be our original x values. So just switching those around. Now, in order to do this, we're dealing with functions, which means when we graph it, we need to pass the vertical line test. So what I mean by that is that we can't graph something like this. That is not a function because that vertical line test, we're crossing it more than once, and we need that rule that for every input, there's only one output. Now, it's a little different with this is that we're thinking of the inverse. So we're thinking of after we switch our x and y values, is that going to be a function? Because then it would be invertible. If I can get this and it passes that vertical line test in this form, it's a function. So taking the inverse is okay. But how do we see that in the original function? When we look at the original function, we want to make sure that that function is 1-to-1. What that means is that each input has a unique output. And how we can test this is with a horizontal line test. So a classic example of a function that's not invertible that we're pretty comfortable with is a parabola. If I inverted this, if I switched my x and y values, what the function would look like, because I could graph it, I could make a table, just switch the x and y, and it would look like this. But that right there is not a function, because that fails the vertical line test. So this is not an invertible function, and how I could see that originally just looking at this graph without going through the process of switching x and y around is if I drew a horizontal line Because when it inverts it, that's really what we're using as a vertical line in that graph. It's switching that kind of behavior. So if we fail horizontally here, we're going to fail vertically here. So that's a way we can check whether or not a function's invertible. All right, so let's just look at some cases here. So we have the function 3x plus 2, and it is 1-to-1. So something that's linear. Linear functions are going to be 1-to-1 because it'll pass the horizontal line test. And we want to find the inverse. So what we could do is we can make a table of values. In that, let's go ahead and just have our x values, our y values, and sorry, instead of y, I'm going to write that as f of x. So let's just use the key points that they're kind of showing on there on the x-axis, -2, 0, 2, 4. And we plug into our function. So -12 plus 2 is -10. -6 plus 2 is -4. 0 plus 2 is 2. 6 plus 2 is 8. And 12 plus 2, 14. All right. So we have some points there. Let's see, we have a 0, 2, and then we have a slope of 3, so I could just use that to graph some points here. There's my -2, -4, and with that, we have a line. All right, so right there is my function f of x. Now what I'm going to do is make a table, but for my inverse function. And all I'm going to do is to get these values is I'm going to switch those two columns there. So I'm going to have a -10. Sorry, I'm not going to write these in red. We're going to have -10, -4, 2, 8, 14 as my x values. And then for x, -4, -2, 0, 2, 4 for the outputs. Let's see, we have a -4, -2, so we're here. We have a +2, 0, and those are the only ones I can graph, but I would have that point there as well, and that point. So my line looks like this. And that's the graph of my inverse function. And I can tell it's a function because it passes that vertical line test. So in terms of making a graph, that's what we're thinking of. Switch the x and y coordinates of your original function, and you can graph the inverse function. Something that's a property of inverse functions is if I graph the line y equals x here, there's this symmetry across y equals x for f of x and inverse f of x. So it's really this reflection over that line as well. But sometimes it's a little difficult to visualize in terms of getting coordinates. This method's best. All right, there were other pieces here that are properties of inverse functions, but I'm going to kind of skip over those because you've learned it before. I just kind of want an overview of pieces we'll come across when dealing with our trig functions. So this one right here, we're looking at a parabola, x² plus 2. So that's a parabola that's bumped up 2 units. So something like this. Now, as I talked about up above there, this is not invertible. So we graphed x² plus 2, and then we want to graph x² plus 2, but only for x more than or equal to 0. So I'm going to graph that on this right-hand side here. So that means I'm restricting my domain. So I'm only going to have that 2, and 3, and 6. So this is what my function would look like only for x more than or equal to 0. So this is x² plus 2, but only for x values more than or equal to 0. Now what we talked about here with our original function, this x² plus 2 is not invertible. And it's because it would fail that horizontal line test. So it fails horizontal line test. So we can't make the inverse of f of x. What we can do is if we limit the domain so that we pass the horizontal line test, which is happening here, then it becomes invertible. So this passes that horizontal line test because what we did is we removed all of those pieces where we would start failing that horizontal line test. So we can make the inverse for this. I'm not going to go through the process of finding the actual inverse function because we won't need that for our purposes, but the fact of recognizing what's invertible and what isn't, and that if we start with a function that's not invertible, we could make it invertible by restricting that domain.